everyone. My name is Lakshmi Thanjalan. I'm a master student, Department of Chemical Technology, Faculty of Science from Chulalongkorn University in Thailand. Today, I would like to present effects of surfactant concentration on surface modification of layer double hydroxides. The outline including introduction, objective, experimental section, result and discussion, and conclusion. The first part is introduction. The surface modification is the first approach to turn physical-chemical properties of solid materials as well as to obtain novel material. Silanes are recognized as efficient copying agents extensively used in composites and adhesive formulation. They have been successfully applied in preparations of mineral fill-less polymer composites. Silane copying agents are chemicals able to form a durable bond between organic material and inorganic material. The example of silane copying agent is aminopropyl diethoxysilane or APS. And the silane can be hydrolyzed to form the silanol group, and then the hydroxy group on the solid surface can condense with silanol group by hydrogen bonding to form silanol network. And also the layer double hydroxide or LDH is commonly used as solid material for the cutting process with silane. The LDH as layers K mineral, the structure is bucite-like layers with the metal hydroxide sheets are stacked to build up layer structure. The divalent metal cation are substituted with divalent metal cation, resulting in a positive charge on the layer. To neutralize this positive charge, an ionic species are present in the interlayer space of LDH. However, the modification of LDH by using chemical coupling of silane copying agent is late because the LDH and silane copying agent have a different hydrophobic property. It makes silanol group difficultly gathered on the LDH surface. Such a problem can be overcome using the anionic surfactant. The anionic surfactant molecule can diffuse into the interlayer space of aldehyde, which allows the interplanar spacing and modify the hydrophobic properties of aldehyde. Besides, and enhances hydrophobic facilitates condensation of silane molecule with the hydroxyl group on aldehyde surface. The next part is objective. In this work, I study the preparation and characterization of magnesium aluminum aldehyde started with aminopropyl diethoxysilane in the presence of sodium dodectin sulfate as an anionic surfactant, and to study the effects of SDS per aluminum molar ratio on physical-chemical property of modified magnesium aluminum aldehyde. This part is experimental section. Firstly is synthesis of magnesium aluminum aldehyde by co-precipitation method. Typically, mixed metal solution were prepared by dissolving of magnesium nitrate hexahydrate and aluminum nitrate monohydrate, corresponding to magnesium per aluminum molar ratio of 3:1 in the eye water, and the preparation of base solution. The sodium hydroxide were refused in the eye water. At room temperature, the mixed metal solution and base solution were dropped into the eye water under stirring and aging at 80 degrees Celsius for 12 hours. The resultant precipitate was filtered, washed, and dyed. The obtained sample was denoted as aldehyde. And secondly, the synthesis of modified aldehyde. The magnesium nitrate hexahydrate and aluminum nitrate monohydrate were dissolved in the eye water to obtain a mixed metal solution, and the base solution was prepared by dissolving the sodium hydroxide and different amount of sodium dodectin sulfate. And the mixed metal solution and base solution were dumped into the eye water. After aging, the resultant precipitate was filtered, washed, and suspended in ethanol. The aminopropyl diethoxysilane or APS were added into the slurry. The obtained sample were denoted as aldehydes, SDS, and APS, where N stands for a molar ratio of SDS per aluminum. The next part is result and discussion. The FT aspecta of aldehydes and modified aldehydes were presented in figure 7. For aldehydes in figure 7a, the important variation were observed in distillate levels. For aldehydes, SDS in figure 7b, the carbonates and nitrates in this chart were strongly decreased and the vibration derived from SDS molecule was observed, such as CH stretching, CH bending, and S-double-O stretching of sulfurous group. For aldehydes, SDS, APS in figure 7D to 7G, when increasing the SDS per aluminium molar ratio from 0.6 to 1.2, resulted in a weakening of carbonate and nitrate band, which suggests the replacement of distinct interlayers and ion with SDS molecule. And the vibration derived from APS molecule were observed in this blue levels. And the next is XRD result to confirm the status of product. The main diffraction peak of aldehydes appearing at 11, 22, and 34 degree according to diffraction plans of 003, 006, and 009 respectively. It can be seen that the aldehydes possesses a hydroxide-like structure in this figure. And well, other layer structure. When adding SDS, the new diffraction peak were observed at around 3 and 7 degree in the figure 9. This explains as an evidence of the reducing surface and ion interlayers aldehydes and suggest that the reducing surface and ionic from vertical intersectional monolayer arranged in the interlayer space of aldehydes, where the sulfurous group were chemical bonded with hydroxide group of aldehydes metal hydroxide layer in this figure. In order to examine the different kind of cyanogen bond formed between APS and aldehydes or the bonding the APS, the silicon NMR was used to assess the silatech product. TN notation are commonly used to describe the number of SiO base. T1, T2, and T3 species were related to monodentate, bidentate, and didentate respectively. In figure 10a, the APS was very an intermolecular bonding without surfactant, resulting in a higher percentage of T2 and T3 signal. This intermolecular condensation of APS can well explain the aggregation of APS on the aldehyde surface in this scheme. When adding the SDS per aluminium molar ratio of 0.6 and 1.2, the relative of T1 signal will increase. This T1 species can explain the dispersion of APS on the aldehyde surface in this scheme. Due to the SDS could hinder the self-condensation of APS, as a result, the APS can have to condense with other ones. Next is the water contact angle test was performed to investigate the surface visibility of silatech aldehydes, as shown in the figure 11. When increasing the SDS per aluminium molar ratio, the water contact angle was increased due to the surfactant can change the aldehyde surface from hydrophilicity to hydrophobicity, which promote the approach of silane to aldehyde surface. And the last part is conclusion. First, the surface modification of magnesium aluminium aldehydes was synthesized by silation procedure with aldehydes incorporated in the SDS and chemical captures APS. And the second, the SDS per aluminium molar ratio of 1.2 was the stable ratio for promoting APS dispersion on the aldehyde surface. And the last is SDS can improve the hydrophobicity of the aldehydes with the SDS per aluminium molar ratio of 1.2 show the highest water contact angle. Thank you for your kind attention.